This will be Chapter 1, Section 6, two-dimensional figures. According to the book, there's a bunch of new vocabulary, and I'm realizing you can pause this and look at it. You can see if there's some words that are familiar. You might be surprised at some of the definitions that I'll show you. A polygon is a closed figure formed by a finite number of coplanar segments called sides. Makes sense? Such that the sides that have a common endpoint are non-collinear, because otherwise it would still be the same side, only longer. And each side intersects exactly two other sides, but only at their endpoints. The vertex of each angle, angle G, angle M, angle L, the vertex of each angle is a vertex of the polygon. A polygon is named by the letters of its vertices, written in order of consecutive vertices. Consecutive means in a row. So here they've named this polygon GHJKLM. Seriously, that's how you name a polygon, with all of the vertices. If I chose to start with point K, then I could have also accurately named this polygon KJHGML. As long as I use all of them and I go in order without skipping around. A poor name for this polygon would be GKMJHL. That's not accurate. Okay, here are pictures of polygons and not polygons, and I got this from the book, but I thought it was very useful. For example, this is not a closed figure. This has an edge hanging off. This where sides intersect each other. Here's a curved side. So these are not considered polygons, and these are all polygons. Even this one right here, which is concave. Normally, we don't even refer to a polygon as convex, but if it's concave, we like to point it out. And concave, it's kind of like it caves in on itself. It's one way to look at it. This is a concave polygon, and the technical definition is listed in the book, and I have put it here in the PowerPoint. Some of the lines pass through the interior. If I drew a line, if I extended the line of each side, like in this triangle, none of the lines go inside the figure, but in this one they do because it's concave. If you don't know here are the lists of commonly named polygons. Let me start with that. And it's expected that you know them, and I'm not really sure when you're supposed to know them, so I'm going to say now. I have now hereby declared that you will know that a 9-sided figure is called a nonagon. So on a quiz, if I said, how many sides does a nonagon have? Then you'll be like, 9. I know it has 9 sides. Okay, so this is something that you could memorize. It's in the book. I copied this from Chapter 1, Section 6, because I found it useful. I liked that. I'll let you read that on your own. An n-gon, yep. When you don't know how many sides it has, you can call it an n-gon if it has n sides. If it has 20 sides, then you call it a 20-gon. N can be replaced with the number of sides. N is another word for number of sides. Word? It's a letter. Okay. Equilateral polygon is a polygon where all the sides are congruent. Lado, equilateral. Equiangular polygon is a polygon in which all angles are congruent. So if it has both, like in this figure, then it's considered regular. That's what a regular polygon, that's the definition, is a convex polygon. So it starts off, if it's concave, this doesn't apply. But if you have a convex polygon that is both equilateral and equiangular, it is called a regular polygon. So here's a couple where we're naming and classifying polygons. This polygon, it says name the polygon by its number of sides. So that's that table I showed you. This polygon right here has 4 sides, so this is a quadrilateral. Then we're supposed to classify it as convex or concave. Well, it's not caving in, so it's convex. Technically, this is how you describe that. I'll let you read that. Push pause if you need to. Regular or irregular. None of the sides are the same length, so it's irregular. Quadrilateral, convex, irregular. That's the name. That's how you can classify and name that polygon. Here's one that's a concave for a different example. And first of all, name the polygon by its number of sides. Well, if you stop and count them, there's 9 of them. There's 9 sides. So this is a nonagon. Here's the technical definition, but I can see that this is like it caves in. So it's concave. And I might say, well, there aren't all 9 sides are different lengths, so it's not, so it's irregular, but also the fact that it's concave makes it irregular. Okay, this is a triangle because there's 3 sides, it's convex and it's regular. This has 4 sides, it's equilateral, it's convex, it's not concave, but it is not regular because the angles are not all the same length measure. The angles are not all the same measure, so it's not equiangular, so therefore it's irregular. This is a table from the book of very common formulas for perimeter, circumference, and area that I'm assuming you're familiar with, and if not, you can easily apply them to any problem. But at the top here, I've added the definition of perimeter and area because I know from the past that students will see the word perimeter and they think they need a formula. And you don't always need a formula to calculate perimeter. You just need to understand the definition is that the perimeter is the sum of the lengths of all the sides of a polygon. In other words, a distance around the figure. So circumference, which is a distance around the circle, that's basically perimeter for circles. And area has to do with the number of square units needed to cover the surface of a figure. Maybe didn't need to leave this example in here. Here's an example of perimeter of a rectangle. I'll click through it quickly to emphasize that the units are centimeters when you get perimeter. When you get area, the units are square centimeters. And of course, you can pause this video at any time if you want to look at the examples closer. Circumference, since circumference is perimeter, the units will be in inches. Since it started in inches, it's not square inches. Circumference is 2 pi r, r is the radius. Radius is half a diameter. The area, in later chapters, you will learn that an exact answer for this problem would be 16 pi. Because as soon as you type pi in a calculator and push enter, now you're rounding to the nearest hundredth or tenth, depending on the problem. But look, the units here are square inches. Okay, now this problem is neat because it's kind of like incorporating different shapes, but it's the concept of this person has 19 feet of tape and they're going to mark off an area. So they have the word area in the problem, but this isn't an area problem. This is a perimeter problem. It says Terry has 19 feet of tape to mark off an area in her classroom or his classroom, in their classroom. Which shape has a perimeter or circumference that would use most or all of the tape? And so they're talking about a square, a circle, a right triangle, and a rectangle of different dimensions, and they want to know which one would be best that would use up almost all of the 19 feet of tape. That's called maximizing the perimeter. So you're asked to compare the perimeters of 4 different shapes, even though up here it has the word area to kind of like, you have to think about it for a minute. Because it says which of she's going to, or they're going to mark an area in the classroom. So they're going to mark off a shape. So the first part they asked you was a square with side length of 5 feet. So here is how you get the perimeter of a square. If there's 4 sides and they're all 5 feet, it's 20 feet in perimeter. A circle with a radius of 3 feet, 2 pi r, which is 6 pi. 6 times 3, 18 point something, 6 pi, 18.85 feet around the circle. A right triangle with each leg length of 6 feet. So you don't know how long the hypotenuse is. If it's a right triangle and each leg length is 6 feet, then that means that the A and the B in the Pythagorean theorem are both 6. It's an isosceles right triangle. Square root of 72 is about 8.49. So then the perimeter would be 6 plus 6 plus 8.49, 20.49 feet. A rectangle with these 2 lengths, the perimeter will end up to be 22 feet. And here's all of your options. And if you recall, the question said the person had 19 feet of tape. So the only shape for which Terry has enough tape is this circle, which is found in part B. And so that is the correct answer.